Your 10-year-old just built something you didn't think was possible at their age. Now you're wondering, what's next? How do you turn that spark into real, industry-ready skill without just adding more screen time to their day? I'm Dr. Priya Mehta, and today we're mapping out the complete journey from age 10 all the way through high school with concrete milestones, technical requirements, and skill progressions that actually prepare kids for engineering, programming, and scientific careers. Welcome to the STEM Lab podcast. Before we get going, just a quick heads up. All the research and writing you're about to hear is human-created and verified, but the voice you're hearing is AI-generated. I want to be upfront about that. If you've been with us for a while, thank you, genuinely. It means a lot that you keep showing up. And if you're new here, glad you found us. We release new episodes every Monday, Wednesday, and Friday, so you've got a steady stream of content coming your way. Now, here's what we're covering today. This isn't about cramming more activities into your child's schedule. It's about building a foundation that connects today's hands-on exploration to tomorrow's professional capabilities. Think of this as your roadmap from curiosity to genuine competence, with alternatives to passive tech consumption built into every stage. Let's start with ages 10 to 12, foundational technical literacy. This is where your child transitions from play-based exploration to purposeful skill acquisition. You're not just looking for engaging activities anymore, you're building a technical foundation that industry tools will later build upon. The developmental window at this age supports abstract thinking and sequential problem solving, which makes it the ideal time to introduce structured learning paths rather than scattered toy experiences. First up, master visual programming before touching text-based code. Block-based environments like Scratch 3.0 teach logic structures, loops, conditionals, variables, without the frustration of syntax errors. Your child should complete 15 to 20 original projects that demonstrate increasing complexity. Simple animations should progress to interactive games with collision detection and score tracking. The LEGO Mindstorms Robot Inventor integrates Scratch-based programming with physical robotics. Check the link below to see the current price. It's got 949 pieces, expandable with standard LEGO Technic elements, and Python programming becomes available after your child masters the blocks. This prepares kids for industry-standard robotic process automation concepts used in actual manufacturing. One heads up, Bluetooth pairing can be temperamental with older tablets, so plan for a dedicated laptop connection. Next, build and program physical electronics with Arduino-compatible platforms. The Arduino Student Kit introduces microcontroller programming through hands-on circuit building. It's recommended for ages 11 and up. Check the link below to see the current price. Your child learns to read datasheets, troubleshoot hardware connections, and write C++ code snippets, not just drag blocks around. It's USB-powered, includes a breadboard and 18 components, and there's no subscription. But consumables like LEDs and jumper wires need periodic replacement. Expect to spend $8 to $12 for a 100-pack of assorted LEDs. This is the same microcontroller architecture used in industrial IoT devices and automotive systems. Projects should progress from blinking LEDs to sensor integration, temperature, light, motion sensors, and eventually to multi-component systems like automated plant watering stations. Expect some initial frustration with circuit debugging. That's not a bug, it's a feature. That troubleshooting process builds real resilience. Now, develop spatial reasoning through parametric 3D design. Tinkercad is browser-based, requires an internet connection, and a free Autodesk account. It teaches constraint-based modeling where dimensions drive design changes. Your child should create at least 30 functional objects, not decorative figures, but things that solve real problems, custom organizers, replacement parts, engineering prototypes. Progress to Fusion 360 Personal by age 12 for assembly modeling and basic stress analysis. It's free for students and hobbyists, but requires account verification, and it only runs on Windows or Mac OS. These are the exact tools used by professional product designers and mechanical engineers. Pair this with a budget FDM printer like the Creality Ender 3 V3 SE. Check the link below to see the current price. It's got a 220 by 220 by 250 millimeter build volume. It can resume printing after power loss, and the enclosed design improves safety but limits visual monitoring. The manual bed leveling can frustrate beginners. Consider upgrading to auto leveling if you're not comfortable teaching mechanical adjustment procedures. Let's talk about learning data collection and analysis with physical science experiments. Spreadsheet literacy. Google Sheets, Microsoft Excel, paired with hands-on experiments, teaches the scientific method with real measurement variability. Your 10-year-old should collect time series data, voltage output from solar panels under different angles, temperature changes during chemical reactions, distance measurements in motion studies. Progress from single variable to multivariable experiments by age 12. The Thames and Cosmos Physics Workshop provides equipment for 285 experiments in mechanics, energy, and electricity. Check the link below to see the current price. Most activities don't require batteries. It's a one-time purchase, and the durable plastic components survive repeated assembly. It's compatible with standard multimeters for electrical measurements. This introduces the data literacy that underpins everything from climate science to financial analysis. One note, the instruction manual assumes adult facilitation. Don't expect independent work on complex experiments just yet. Moving on to building working renewable energy systems from components. Move beyond pre-wired kits to systems your child assembles from discrete components: solar cells, charge controllers, batteries, LEDs. The difference matters. Troubleshooting connections teaches electrical theory that plug-and-play kits hide. Projects should progress from simple solar-powered circuits to wind turbine designs with blade optimization experiments to hybrid systems with energy storage. This requires a soldering station, 15 to 30 watts with adjustable temperature, adult supervision required, around $30 to $40 for beginner models, plus a digital multimeter for voltage, current, and resistance testing, and basic hand tools. This is the same system design thinking used in grid-scale renewable energy installations. Here's something important. Practice screen-free computational thinking before adding more devices. Yes, I'm a psychologist advocating for less screen dependence even as you're building technical skills. Think Fun Robot Turtles and similar unplugged coding games teach algorithm design, debugging, and optimization without batteries or Wi-Fi. Check the link below to see the current price. Your child should spend 20 to 30% of STEM time in screen-free problem solving. It builds executive function and reduces the dopamine dependency that makes focused work harder later. These games are one-time purchases with no consumables, they work anywhere, and they prepare children for the mental models they'll apply in text-based programming. Don't skip this next part. Document projects in engineering notebooks. This isn't busy work, it's professional practice. Your child should maintain a physical notebook, grid paper preferred, around $8 to $12 for lab-grade notebooks, with dated entries showing design decisions, failed attempts, and iterative improvements. Photographs, sketches, and data tables belong here. This is identical to the documentation practices required in patent applications, research publications, and engineering design reviews. By age 12, entries should include hypothesis statements, control variables, and quantitative comparisons between design iterations. Here's the key. Complete skill milestones, not just projects. Don't just count finished builds, track capabilities. By age 12, your child should independently write and debug 100-plus lines of block-based code, solder 20-plus successful connections, design and print 10-plus functional objects, collect and graph multivariable datasets, and explain system failures using technical vocabulary. These are the concrete outcomes that matter. Now we're moving into ages 13 to 15, intermediate technical competency. Middle school is where your STEM learning path matures into genuine technical competency. Your teenager isn't just following instructions anymore. They're making design decisions, selecting appropriate tools, and evaluating trade-offs. The cognitive development at this stage supports hypothetical thinking and systematic problem solving, which means you can introduce industry-standard complexity without overwhelming them. Transition from block-based to text-based programming languages. Python 3.11 or higher becomes the primary language for ages 13 and up. It's free, runs on any operating system, and works offline with downloaded libraries. Your teen should complete 40 to 50 original programs demonstrating file input and output, data structures like lists, dictionaries and sets, basic algorithms like sorting and searching, and API integration. Start with console applications, then web scraping, then data visualization with matplotlib. This is the most in-demand programming language in data science, machine learning, and scientific computing careers. Pair Python learning with physical computing using Raspberry Pi single-board computers. They've got quad-core processors, 2 to 8 gigabytes of RAM depending on the model, around $35 to $75, GPIO pins compatible with Arduino sensors, and they run a full Linux operating system with thousands of free software packages. Master version control and collaborative development practices. Git and GitHub teach the workflows that every professional software team uses. Free accounts, requires internet for syncing, works on any operating system. Your teen should maintain repositories for all coding projects, write meaningful commit messages, create branches for experimental features, and practice merge conflict resolution. This isn't about complex teamwork yet. It's about building the habits that make collaboration possible later. These are non-negotiable skills for anyone pursuing software engineering, data science, or any technical career involving code. Design and fabricate multi-material prototypes. Advance beyond single-material 3D printing to projects combining printed components with metal hardware, electronics, and off-the-shelf parts. Your teen should design assemblies with proper tolerances, typically 0.2 millimeter clearance for FDM prints, specify fasteners, and create bill of materials documentation. Projects like functional RC vehicles, automated measurement instruments, or assistive devices for people with disabilities require systems thinking across mechanical, electrical, and software domains. This requires calipers with 0.01 millimeter resolution, around $20 to $25, a tap and die set for creating threaded connections, and basic metalworking tools. This is the integrated product development approach used in consumer electronics and medical device manufacturing. Learn PCB design and professional electronics fabrication. Move from breadboard prototypes to printed circuit boards using KiCad. It's free, open source, runs on Windows, Mac OS, or Linux. No subscription. Your teen should design schematic diagrams with proper component symbols, create PCB layouts with appropriate trace widths and clearances, and generate Gerber files for manufacturing. Services like JLCPCB or PCBWay fabricate custom boards for around $5 to $15, including shipping, with a 3-week turnaround. This requires understanding surface mount versus through-hole components, power distribution planning, and signal integrity basics. This is the same PCB design process used in smartphones, automotive electronics, and industrial control systems. Initial designs will have errors, misaligned footprints, incorrect power ratings, which is exactly why this learning stage matters. Implement machine learning models with real datasets. Python libraries like scikit-learn enable your teen to train classification and regression models using actual data. It's free and works offline after installation. Projects should progress from pre-cleaned tutorial datasets to messy real-world data requiring cleaning, feature engineering, and validation. Start with supervised learning, predicting house prices, classifying images, before attempting unsupervised approaches like clustering customer data or dimensionality reduction. The goal isn't mathematical mastery, it's understanding when machine learning applies, how to evaluate model performance, and what training actually means. This prepares students for the AI and ML engineering roles that dominate current tech hiring. Participate in structured robotics competitions. VEX Robotics Competition or First Tech Challenge provides standardized challenges that reveal gaps in your teen's skill set. VEX requires team registration around $100 to $150, RobotKit around $300 to $500. VEX V5 uses C++ or Python programming, requires a rechargeable battery, around $80 replacement, and has an extensive aluminum structural system for custom designs. FTC requires team registration around $275, RobotKit around $400 to $600. FTC uses Android phones as controllers. You can program with blocks or Java, and it allows more flexible design approaches. Both competitions require sustained iteration cycles. Your teen will rebuild mechanisms 5 to 10 times before finding workable solutions. That persistence under time pressure is the real education.
Master oscilloscope operation and signal analysis. Digital oscilloscopes teach time-domain signal analysis, essential for debugging circuits and understanding communication protocols. Entry-level USB models run around $80 to $120. Standalone bench models around $300 to $400. Your teen should measure voltage waveforms, identify noise sources, decode PWM signals, and verify timing relationships. You need 2 or more channels, 50+ MHz bandwidth for basic work, trigger controls, and measurement cursors. This is the primary diagnostic tool in electronics repair, embedded systems development, and RF engineering. Projects should include analyzing Arduino PWM outputs, debugging I2C communication timing, and measuring switching power supply ripple. Complete certification track learning in one specialization. Rather than shallow exposure to many topics, your teen should pursue depth in one domain: robotics, electronics, software development, or CAD and manufacturing. Complete structured curricula, not random projects, that culminate in portfolio pieces demonstrating professional adjacent competency. For software, build a multi-page web application with database backend. For electronics, design and fabricate a custom PCB with microcontroller and sensors. For CAD, create a complete product design with assembly instructions and manufacturing specifications. These portfolio pieces directly support college applications and internship opportunities. By age 15, build a complete system project integrating multiple disciplines. Your teen should complete one ambitious project requiring 60+ hours that combines programming, electronics, mechanical design, and data analysis. Examples: weather station with custom sensors logging to a cloud database, autonomous robot navigating using computer vision, IoT greenhouse with automated climate control, or renewable energy monitor comparing solar and wind generation patterns. This requires dedicated workspace with stable power, internet connectivity for cloud services, and secure storage for works in progress. This systems integration thinking mirrors professional engineering project workflows. Now we're at ages 16 to 18, pre-professional technical proficiency. High school students on a STEM learning path that started 6 years ago are now competing with college sophomores in capability. Your teen can tackle professional adjacent projects, use industry standard tools fluently, and make informed specialization decisions. The goal here isn't college admission padding, it's building genuine expertise that provides day-one value in internships, research positions, and technical work. Master advanced programming paradigms and software architecture, object-oriented design, functional programming concepts, asynchronous operations, and API design patterns should all be comfortable territory by age 17.
Your team should build applications with 2,000 plus lines of code demonstrating separation of concerns, reusable components, error handling, and documentation. Languages should expand beyond Python to include JavaScript for web development, C or C++ for performance-critical code, or language specific to their specialization, R for statistics, MATLAB for engineering. This requires development environment setup with linters, formatters, and testing frameworks, the same toolchain professional developers use. Projects should include automated test suites with 60% or higher code coverage. Contribute to open-source projects and professional code reviews. Find beginner-friendly GitHub repositories, look for good first issue labels, submit pull requests, and respond to feedback from maintainers. This teaches professional collaboration standards. Your team will experience the gap between working code and production-ready code, proper error handling, edge case coverage, documentation, and code style consistency. This experience is more valuable than most computer science coursework for actual software careers. Expect initial pull requests to be rejected. The feedback is the education. Expect initial pull requests to be rejected. The feedback is the education. Design custom tooling for specific scientific applications. Rather than using off-the-shelf lab equipment, your team should build specialized measurement instruments, data acquisition systems, or automation tools for specific research questions. Examples: spectrophotometer using photodiodes and LED arrays for water quality analysis, precision motion control system for time-lapse microscopy, or custom data logger for environmental monitoring. This requires integration of analog sensors, signal conditioning circuits, analog to digital conversion, and calibration procedures. This is the instrumentation engineering approach used in research labs and specialty manufacturing. Learn industry-standard CAD tools beyond educational versions. Transition from Fusion 360 Personal to SolidWorks, student license, around $100 per year, or Siemens NX, free student license, used in aerospace, automotive, and industrial design. Your team should complete assemblies with 50-plus parts, create technical drawings with geometric dimensioning and tolerancing callouts, and perform finite element analysis to predict stress concentrations and failure modes. This requires a Windows machine with dedicated GPU, minimum 2 GB VRAM, 16 GB system RAM recommended. These simulation capabilities prevent expensive physical prototyping failures, the same approach used in professional mechanical engineering. Implement embedded systems with real-time operating systems. Move beyond Arduino's simple loop structure to FreeRTOS or Zephyr RTOS for multitasking, priority scheduling, and resource management. Your team should design systems with multiple concurrent tasks, motor control running at 1 kHz, sensor reading at 100 Hz, display update at 10 Hz, wireless communication at 1 Hz, all executing reliably. This requires microcontrollers with sufficient RAM, minimum 64 kilobytes, 256 kilobytes or more preferred, hardware timers and interrupt controllers. This is the embedded systems architecture in automotive ECUs, industrial PLCs, and IoT gateways. ESP32-based development boards, around $8 to $15, provide dual-core processors, Wi-Fi and Bluetooth, and extensive peripheral support. Complete advanced manufacturing processes beyond FDM printing. Resin 3D printing produces parts with 25-micron layer resolution suitable for jewelry casting, dental models, and engineering fit testing. A complete setup runs around $250 to $400. CNC routing enables subtractive manufacturing in wood, plastics, and soft metals. Desktop models run around $300 to $800 for entry-level. Resin printing requires dedicated ventilation for VOCs during printing, IPA or specialized cleaning solution as an ongoing consumable, around $15 to $20 per gallon, and UV curing for 2 to 5 minutes. Safety protocols are non-negotiable. Uncured resin is a skin sensitizer requiring nitrile gloves. This adds manufacturing versatility that complements additive processes, matching prototyping workflows in product development studios. Develop machine learning systems with neural networks. TensorFlow or PyTorch frameworks enable your team to train deep neural networks for computer vision, natural language processing, or time series prediction. They're free and GPU accelerated with NVIDIA CUDA support. Projects should use real data requiring collection, labeling, augmentation, and validation, not just tutorial datasets. Training complex models requires a GPU with 4 GB or more VRAM, desktop cards preferred over laptop GPUs, around $300 or more for a used RTX 3060 or cloud computing credits. Google Colab free tier provides limited GPU access, paid tiers around $10 per month. Your teen should understand overfitting, learning rates, batch normalization, and architecture selection, not just copy tutorial code. This is the foundation of current AI engineering roles in computer vision, recommendation systems, and autonomous vehicles.
Pursue industry certifications or dual enrollment technical coursework. CompTIA Plus, around $250 per exam, 2 exams required, provides IT fundamentals certification. Cisco CCNA, around $300 exam, covers networking. Autodesk certified user exams, around $125, validate CAD proficiency. AWS Cloud Practitioner, around $100 exam, demonstrates cloud computing basics. These certifications carry weight with employers and provide structured curricula beyond self-directed learning. Alternatively, dual enrollment courses at community colleges, often free or low cost for high school students, in electronics, programming, or engineering, provide transferable credit plus access to professional equipment like PCB fabrication, CNC machines, and test instrumentation. Certification exams require proctoring, online or test center, typically 90 to 120 minutes, passing scores around 70 to 80%. Build a professional portfolio demonstrating employable skills. By age 18, your teen should maintain a portfolio website, free hosting on GitHub Pages, Netlify, or Versal, showcasing 8 to 12 substantial projects with documentation, source code, demonstration videos, and technical write-ups. Each project should clearly state the problem solved, technologies used, challenges overcome, and quantitative results where applicable. This portfolio supports college applications, scholarship competitions, internship applications, and early career positioning. Professional presentation matters: clean layouts, proper grammar, functional links, and responsive design for mobile viewing. Let's talk about technical infrastructure, building your progressive STEM learning path. The physical setup supporting your STEM learning path evolves significantly from age 10 to 18. You're not building a playroom, you're creating a functional technical workspace with real infrastructure requirements. This isn't about spending excessively, but rather about strategic investments that grow with capability. Workspace requirements by skill stage. Ages 10 to 12. Shared dining table or corner desk works fine. Minimum 4 feet by 2 feet surface area. Requires 1 electrical outlet, good lighting, and storage bins for components. No dedicated room needed yet. Ages 13 to 15, dedicated workspace becomes important. 6 feet by 3 feet desk preferred. Requires multiple electrical outlets with surge protection, minimum 6 outlet strip, task lighting like an adjustable LED desk lamp, pegboard or shelving for tool storage, and a ventilated area for soldering near a window or with a small fan. This workspace can be bedroom-based but needs clear boundaries from sleep and relaxation areas. Ages 16 to 18. Workshop or garage space preferred. Minimum 8 feet by 6 feet area. Requires a 15-amp dedicated circuit for power tools and 3D printer operation. Proper ventilation system for resin printing or CNC work with a window exhaust fan minimum or ducted ventilation preferred. An ESD-safe workbench mat around $25 to $40,
and secure storage for hazardous materials like adhesives, solvents, and resins. Climate control matters. Avoid extreme temperatures that affect electronics and filament storage. Computing requirements progression. Ages 10 to 12. Entry-level laptop sufficient. Chromebooks have limitations. Arduino IDE requires workarounds. Fusion 360 is unavailable. Windows or Mac OS preferred. Minimum 8 GB RAM, 256 GB storage, around $400 to $600. Internet required for cloud-based tools like Tinkercad and Scratch Online. Ages 13 to 15. Mid-range laptop or desktop, 16 GB RAM, dedicated graphics preferred for CAD, 512 GB SSD minimum, around $700 to $1,000. Offline capability becomes important for programming, CAD, and electronics work. Ages 16 to 18. Desktop workstation ideal. 32 GB RAM, discrete GPU with 4 GB or more VRAM for ML training, 1 TB or more SSD for datasets and VM images, around $1,200 to $1,800 for a DIY build or refurbished workstation. Dual monitor setup improves productivity for code plus documentation or CAD plus reference materials. Tool acquisition timeline. Don't buy everything at once. Match tools to current skill level to avoid overwhelming early learners and justify costs as capabilities develop. Year 1, age 10 to 11, basic hand tools like screwdrivers, pliers, wire cutters, around $30 to $40 set. Digital caliper around $15 to $25, simple multimeter around $15 to $20, safety glasses, work gloves. Year 2, age 11 to 12, soldering station with temperature control around $40 to $60, helping hands or PCB holder around $8 to $12, flush cutters for electronics around $8 to $15, breadboard and jumper wire sets around $20 to $30 combined. Year 3 to 4, age 13 to 14, budget 3D printer around $200 to $300, filament storage containers with desiccant around $20 to $30, oscilloscope, USB, or entry-level bench around $100 to $150, power supply with adjustable voltage and current around $60 to $100. Year 5 to 6, age 15 to 16, resin printer setup, if needed, around $250 to $400 complete. Hot air rework station for SMD work around $60 to $100. Bench vise around $40 to $80. Additional measurement tools like LCR meter or function generator around $50 to $100 each. Year 7 to 8, age 17 to 18, specialized tools matching chosen specialization, CNC router, laser cutter access through makerspaces often for around $50 to $100 per month membership, professional development boards, advanced test equipment. Consumables budget planning. Ongoing expenses vary dramatically by focus area, but expect this. Annual consumables ages 10 to 12, around $150 to $250 for Arduino components, batteries, craft supplies, replacement parts. Annual consumables ages 13 to 15, around $300 to $500 for 3D printer filament, averaging 4 to 6 kilograms per year, electronic components, PCB fabrication, project-specific materials. Annual consumables ages 16 to 18, around $500 to $800 or more for specialty filament, resin, CNC tooling, larger component orders, cloud computing credits, certification exam fees. These are working budgets, not minimums. Your team is actively building, which means materials get consumed. Safety equipment is non-negotiable. Safety glasses rated ANSI Z87.1 around $12 to $20,
Nitrile gloves for resin and chemical handling, 100-count box around $8 to $12. Fire extinguisher, 5-pound ABC rated around $20 to $30. Check pressure gauge annually. First aid kit with burn treatment supplies around $20 to $30, and proper ventilation for any process producing fumes. This isn't helicopter parenting, it's the same personal protective equipment required in professional labs and makerspaces. One severe burn or chemical exposure can end STEM enthusiasm permanently, so enforce protocols consistently. Expandability matters more than initial capability. Choose platforms that grow through additions rather than replacements. Arduino ecosystem expands through shields and sensors. Raspberry Pi works with countless hats, hardware attached on top. Lego-compatible robotics integrate with a massive parts inventory. Modular 3D printers accept upgraded hot ends, direct drive extruders, and larger build plates. This expandability reduces waste and maintains compatibility with earlier projects. Your teen isn't starting over every 2 years. Here's your final check before you go. Use this condensed checklist to evaluate your current position and identify next steps.
Foundation stage, ages 10 to 12. Child completes 15 or more original Scratch projects with increasing complexity. Physical programming platform like Arduino or compatible used weekly. 3D design software like Tinkercad minimum used to create 20 or more functional objects. Screen-free coding activities balance digital work, 20 to 30% of STEM time. Engineering notebook maintained with dated, documented projects. Basic electronics toolkit acquired, multimeter, breadboard, components. At least one multi-week project requiring iterative debugging completed. Intermediate stage, ages 13 to 15. Python proficiency demonstrated through 40 or more original programs. GitHub account active with multiple repositories showing commit history. Text-based programming, Python, C++, or JavaScript is primary development mode. PCB design software like KiCad used to create at least one custom board. Oscilloscope or logic analyzer used for circuit debugging. Machine learning basics explored with actual dataset training. Portfolio includes 3 to 5 substantial projects with documentation. Robotics competition participation or equivalent structured challenge experience. Advanced stage, ages 16 to 18. Professional-grade CAD software fluency, SolidWorks, NX or equivalent. Code contributions to open-source projects or similar collaborative development. Deep neural network training experience with TensorFlow or PyTorch. Advanced manufacturing beyond basic FDM printing, resin, CNC, or injection molding. Industry certification earned or dual enrollment technical coursework completed. Professional portfolio website demonstrates employable skills. One ambitious integration project, 60+ hours completed independently. Clear specialization focus identified with depth in that domain. Infrastructure checklist. Dedicated workspace appropriate for current skill level established. Computing resources meet requirements for current software tools. Safety equipment, glasses, gloves, ventilation, fire extinguisher, in place. Tool inventory matches current capabilities, not over or under-equipped. Consumables budget covers active project work without constant restrictions. Storage solutions keep components organized and accessible. Internet connectivity stable enough for cloud tools and research. Missing items aren't failures, they're your next steps. Some frequently asked questions. What if my 10-year-old is already advanced in one area but not others? Depth beats breadth at every stage of learning. If your child excels at programming but hasn't touched electronics, let them build programming mastery to the intermediate level before forcing hardware integration. The underlying computational thinking transfers easily once they're ready. Conversely, children who love building physical systems but resist coding can develop mechanical and electrical expertise first. The programming motivation often appears naturally when they want to automate something they've built. Watch for genuine interest signals rather than forcing balanced development across all domains. How much daily or weekly time should a child spend on STEM activities for this learning path? Consistency matters more than total hours. 3 focused 45-minute sessions per week, around 2.5 to 3 hours total, produces better learning than one marathon weekend session. For ages 10 to 12, that's sufficient for steady progress. By ages 13 to 15, increase to 4 to 6 hours weekly as projects grow more complex and require sustained debugging sessions. Ages 16 to 18, pursuing technical depth, typically invest 8 to 12 hours weekly, especially when working on portfolio projects or competition prep. These aren't screen time limits, they're active building and problem-solving hours. Balance this with physical activity, social time, and unstructured play. If your child resists STEM time consistently, the activities don't match their interests or skill level. Adjust rather than push through. Should we follow this learning path sequentially or skip stages if my child picks things up quickly? Capability milestones matter more than age gates. A precocious 11-year-old demonstrating genuine Python proficiency, not just copying tutorials, should absolutely progress to intermediate challenges rather than artificially waiting for age 13. However, verify the foundational skills are truly solid. Can they debug unfamiliar problems, explain their design decisions, and adapt solutions to new contexts? Skipping ahead with shallow understanding creates frustration when advanced projects require those missing foundations. The reverse applies too. 13-year-olds still mastering block-based programming aren't behind. They need foundation work, not pressure to match arbitrary age expectations. Use the capability checklists rather than ages as your progression criteria. Final thoughts. The STEM learning path you're building today isn't about creating child prodigies or padding college applications. It's about giving your child the practical competency to shape the world they'll inherit. You're teaching them that systems can be understood, tools can be learned, and complex problems yield to patient iteration. That confidence, the bone-deep belief that I can figure this out, matters more than any specific technical skill. The path from scratch animations to neural network training seems impossibly long when you're at the beginning. But you're not climbing in one leap. You're taking consistent steps. This week's Arduino project, next month's 3D print, next year's robotics challenge. Those steps accumulate into capabilities that genuinely prepare young people for technical careers and informed citizenship in an increasingly complex world. Your role isn't to master these technologies yourself, it's to provide the infrastructure, remove the obstacles, and celebrate the small victories that build momentum. Some weeks you'll feel behind the timeline. Some projects will fail spectacularly. That's the process working exactly as designed. The failure is where the learning lives. Give your child the tools, the time, and the space to build. They'll show you what they're capable of becoming. That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. We drop new episodes every Monday, Wednesday, and Friday, so you've always got something fresh to check out. If you're finding value in what we're doing here, I'd be really grateful if you could leave us a 5-star rating and write a quick review. It's honestly the best way to help other people discover the show when they're searching for this kind of content. And make sure you hit subscribe or follow so you get notified the second a new episode goes live. I'll catch you next time.